This is part 2 of lecture 7 of ELEC 5300. We introduced the idea of maximum likelihood estimation, and now I'd like to go through some examples. And in this section we'll just be looking at examples where we just have to estimate a single parameter, usually the mean. And hopefully this will give you an idea that even though we had to introduce this log to make the product into the sum when we looked at the log likelihood, introducing that log is actually a really useful thing. So let's take a look at our first example. That's a univariate Gaussian with unknown mean. So this is exactly the problem we looked at in the last part, where we had that Gaussian hill, and we're just kind of shifting the location of the hill, but the width of the hill, the variance, remains constant. So our density then is this exponential or Gaussian density that contains this exponential, and the fact that it contains that exponential should give you a hint that, hey, actually maybe taking the log wouldn't be that bad, because we know that when we take the log of the exponential, we just get they cancel each other out. So if we have log of the exponential of x, right, then we just get x. Okay. And so now in this case we're going to get a very intuitively satisfying result that the maximum likelihood estimate of the mean is just the sample mean. So we just take all of the data points that we have and we just average them together. And that's consistent with an intuition that we introduced last time when we said that we want to put that mean somewhere in the middle of all the data points, and the sample mean is a good definition of the middle. So let's actually prove that that's the case, and we'll see here how the log really helps us out. So our data then is x1 through xn. By independence, we can say the probability of the data is just the product of the individual probabilities of each data point looked at individually. Now when we take the log, again what happens is that the product here becomes a sum, right? And because if, let's say, I call this thing A and this thing B, then because log of A times B is equal to log of A plus log of B, right, then I just get this plus this. And so because I've taken the sum, I get n of these. So I get n of log of 1 over something, but because log of 1 over A is just minus log of A, right, then I get the minus sign here. So I get n log of the denominators here, and I get a minus sign because I'm taking the denominator. And then when I take log of this thing here, then like I told you before, the exponential and the log cancel out, and so I just get minus these guys, and I'm just going to, the product here becomes the sum. So I get the sum of all of these guys inside here. Now what I can do is I can differentiate with respect to theta, and because theta only appears in the second part, when I take the derivative, this thing disappears. So I can forget about this thing here, and I just get the derivative of this, and I can move the derivative inside the sum, so I get the sum. I can take the sigma squared outside, so I get 1 over sigma squared on the outside, and I differentiate this with respect to theta, and I just get 2, which is canceled by the 2 down here, x minus theta, right? So I get x minus theta inside here, and I can take the sum and I can apply it to all of the thetas, and I just have n thetas, right? So I get the sum here, so I'm going to do this first, the sum of the x's minus n of the thetas here. Now what I can do is I can set this whole thing equal to 0, and so in order for this thing to be 0, because the variance is positive, that this thing has to be 0, which then implies that this has to be equal to this, or in other words, theta, the optimal value of theta is just 1 over n times the sum of all the data points, or the sample mean. Okay, so that's the proof that the maximum likelihood estimate of the mean is the sum. And this is true for other random variables as well. In this example here, we'll take a look at the exponential random variable. Right, so now we're going to assume that the observations are taken from an exponential density, and the exponential density is determined by this parameter lambda. Right, so if you remember what the exponential distribution looks like, it's lambda e to the minus lambda x for x greater than 0, so we can put a unit step function there. And so the peak value here is lambda, and then it just decays as e to the minus lambda. Okay. And so the larger the value of lambda is, right, let's say if I get a larger value of lambda, then it starts out higher, right, but it decays faster. Right, so that's for a larger value of lambda. And so the larger the value of lambda is, right, the lower the mean is. Right, so here, in fact, if you go to any basic probability textbook, it will tell you that the expected value of x, the mean of x, is 1 over lambda. So it's inversely proportional to lambda. And you can figure that out yourself just by doing the integral if you want. So here we have to assume that all the xk's, the data points, have to be greater than or equal to 0. Otherwise, the data is inconsistent with the exponential distribution. And once we have a negative value here, then the probability distribution will be 0 no matter what, and there's nothing we can do. So all the x's have to be bigger than 0. And then again, by our independence assumption, the probability of all of the data points is just the product of the individual probabilities. I don't have to worry about this u of x because I've assumed that all the data is greater than or equal to 0. And then I, again, take the log. Right? So when I take the log of f d given lambda is equal to the sum of the log of these. So we get the log of lambda, right, minus lambda xk. Right? So that's again just the product. The log of the product is the sum of the logs, and the log undoes the exponential. Right? And so now again we see this really nice property of the log removing that nasty exponential that we got there. And so now when we differentiate this thing, we take this and we differentiate it. Now remember here we're summing over k, so we just get n of these log lambdas. So here this is, I'm going to take this thing and move it down into here. I get n of the log lambdas, and I can take the lambda outside the sum here, so I get lambda times the sum. And I differentiate with respect to lambda, right? And so you know that if I take d dx of log of x, I get 1 over x. Right, so I get 1 over lambda when I do that derivative, or n divided by lambda, minus lambda, the derivative of this, lambda times something, and I just get the something. So minus this something here. And now setting this thing equal to 0, I know that this thing has to be equal to this thing. Therefore, n divided by lambda has to be equal to the sum, right? Or 1 over lambda, the maximum likelihood estimate of lambda is just 1 over this, which is the sample mean, right? And 1 over lambda, remember, is the mean, the estimate of the mean. So again, what we're trying to do here is estimate the mean by the sample mean. Okay, and so this is a general strategy. It's not always the maximum likelihood strategy, but sometimes when you have these kinds of things, you just try to match the means of the variances of the assumed distribution and the data, and that's called moment matching. That's one way you can do parameter estimation, and in some cases it's this exact same thing as you would get with maximum likelihood, but not always. Now, the distributions that we looked at just now were all for continuous random variables, but this technique is also applicable to discrete random variables. And so let's take a look at an example of that. There's nothing more discrete than the Bernoulli random variable. There's only 2 values, either 0 or 1. And usually what we have is that the probability mass function now is either equal to some probability mu, right? And I'm going to use mu here because it turns out that mu is the same as the mean. But this is a probability between 0 and 1. And so the probability is mu if x is equal to 1, and 1 minus mu if x is equal to 0. Right? Now, the unknown parameter now here is mu, right? But kind of like taking the log of this kind of expression here is a little bit difficult, right? Because it's not really in the form that we have like a single expression that we can use. But it turns out that this is completely equivalent to this expression over here, which at first glance looks a lot more difficult, right? But in fact has a lot of nice properties, as we'll see. Okay, so here if I set x is equal to 1 in this expression, then I get a 1 here, so I just get mu times something to the 1 minus 1 or 0. So whatever to the 0th power is just 1, so this becomes 1 when x equals 1, and I just get mu. Right? When x is equal to 0, I get mu to the 0, which is 1, and 1 minus mu to the 1 minus 0, or 1, and so I just get 1 minus mu. So these two things are exactly the same at these 2 points, x is equal to 0 and x is equal to 1, but those are really the only 2 points that we care about. So now assuming we have a bunch of training data here, x1 through xn, and these are all either 0 or 1. So you can imagine we flipped a coin and we got either heads or tails, and we want to know the probability of heads in that coin. And now we can take the likelihood, which is just the product over all the individual probabilities, right? And then when we take the log likelihood, right, we just end up converting this product into a sum, and then when we take the log of a to the x, right, we just get x times log of a. Right. And so now, even though the x's here kind of appeared in the exponent here, again we get this nice property that the log kind of undoes that exponentiation. Right. And so now the x here is here, and I just multiply by log of a. Right. And so here, if I have mu to the x, right, then I just get x times log of mu, and then this product here becomes a sum plus the log of this, which is just 1 minus x times the log of 1 minus mu. Right. Now I differentiate this thing with respect to mu, and remember, whenever I differentiate with respect to mu, or whenever I differentiate the log, I just get 1 over mu, so I get x over mu, right, and then I get 1 minus x divided by 1 minus mu, and I get a minus sign here due to the chain rule, because I'm differentiating with respect to mu here, and I have a minus sign in front of that, so I get the minus sign due to the chain rule. Now what I'm going to do is I'm going to set this thing equal to 0, but before I do that I have to do a little bit of manipulation of the thing that I got in here. I want to put the two things here on top of the same numerator, mu times 1 minus mu. And so in order to do that, I multiply this by 1 minus mu, right? And I multiply this thing here by mu, and then I add them together with the minus sign here, so I get that. And then here you can see there's a cancellation here. What I get is a mu x here, right, and a minus mu x here. So I get a mu x, a minus mu x plus mu x. So this thing cancels out, this thing cancels out. Now all I get is a 1 times x, or xk, minus mu times 1, or mu. Right? And in order for this thing to be equal to 0, I really only care about the numerator here, right? Because the denominator here is fixed, and for mu between 0 and 1, it's always some positive value. Okay, so I don't have to worry about this, and so all I really have to do is set summation of k is equal to 1 to n of xk minus n mu. Right, so I've just summed these guys together, and I've done the summing already by just taking n of these guys. So instead of having the sum around the mu, I've taken the mu's outside, set that thing equal to 0, and so mu is equal to 1 over this. So again, this is the sample mean. Right, so the best estimate of mu, which is the mean of the distribution, is simply the sample mean. So again, we get this idea of mean matching or moment matching. Now, that's not always going to be the case. That maximum likelihood will give us something that results in trying to match the mean. And so to see that, let's take a look at the uniform density. So for the uniform density, we have something which is uniform on 0 to m, and we're going to assume that here the maximum value of the uniform density is unknown, because we only want to deal with one parameter right now. So here, depending on what the value of m is, right, I get a different distribution, and in order for this to integrate to 1, I have to have the height of this thing be 1 over m, and so for smaller values of m, right, what I would get is larger values of the distribution, and then outside this range, of course, it's 0 here and 0 over there. And so then the question is, what's the maximum likelihood estimate of m if I have a set of data? Here, again, I have to assume that they're all greater than or equal to 0. And obviously, you'd also expect m here should be bigger than the largest value of the data, right? Because otherwise it wouldn't make any sense, right? So let's take a look at what we get from this example. So again, we take the product of all the individual probabilities, but here, as long as the data is inside this region, so suppose we had some data points inside here. I'm just going to draw in some data points here. All of these data points have the same height, right? So it's all 1 over m, and if I have n data points, right, then I just have 1 over m times itself n times, or 1 over m to the nth power, right? And again, I have to have all the data points in between here, so I can't assume that m is smaller than the largest data point. And so then what we want to choose is we want to choose the smallest possible value of m, right, in order to maximize the likelihood, right? Because the smaller the value of m, the larger the 1 over m to the n is, right? And so what I want to do is I want to take this m down, and as I move the m down, so let's redraw this. So here's my data points. As I move the m down, then, as we saw before, what will happen is that the height will increase, right? So if I had a value of m, let's say, like this, then I might get a relatively low value here. And so if I decrease the value of m to down to here, then it would go up a little bit, right? If I went down to here, it would, let's say, go up to here, right, and so on, right? And so I go up to here, like this. And then what I want to do is keep on moving this down, because then the length of all these lines that connect x to these points here, let's say this is the tallest one, keep on getting higher and higher. Right? But then I don't want to pass this highest point here, because the minute I pass that highest point here, let's say I have a distribution that's given by this orange thing here. So this would make all these guys longer, but then, because remember it's 0 inside here, I would take all these longer lines here and just multiply it by 0. So that would result in 0. So I'm going to move the m all the way down until it just touches this point here, but go no further than that, right? And so what that means is that ml should be equal, the maximum likelihood estimate of m should be the maximum value of xk, right? And so here, if I looked at the mean, right, the mean of the distribution is just m divided by 2, right? So the maximum likelihood estimate of the mean is half the maximum value in the data set, and that's not the same as the sample mean. So ML doesn't always result in the mean being equal to the sample mean, even though it in many cases it turns out to be the case. Now, if I have a multivariate Gaussian, right, with an unknown mean vector, right, then actually I have a multivariate problem, because I have, let's say if I have an n-dimensional Gaussian, I have n unknown parameters, right. But intuitively, you could expect that basically the same thing is going to happen, and then so it turns out that I can solve this, and I'll look at some other examples for solving these kinds of things here. But just kind of intuitively, it shouldn't be surprising to you that the mean is indeed equal to the sample mean. Okay, so that's the case for the multivariate Gaussian. But in order to prove that, we have to do some extra work because things become more complicated. So we'll look at that next time.